All right, so our second speaker for the session will be Marcus Pivato, who will tell us about universal recursive preference.
Okay, so thank you all for coming, and thank you very much to the organizers for putting this together and inviting me. So I'm going to be talking about universal recursive preference structures. So what exactly are those? To start, I think probably I should talk a little bit about sort of the way that economists think about rationality, right? So what does rationality mean in economics? So in economics, the standard notion of rationality basically is based on agent of preference. So every agent is endowed with a preference order. And by a preference order, I mean a complete transitive binary relation, typically indicated like this, on the set of possible outcomes or alternatives or whatever, right? And so when you have two outcomes, X and Y, then this relation here, X related to Y, we read that as the agent prefers X to Y. So given a choice between X and Y, the agent would choose X normally. And given some menu of outcomes, rationality consists in choosing the best item from that menu. So a rational agent will choose the item from the menu which is preferred to every other item on the menu, which maximizes their preference, right? Now, in some contexts, the outcomes have a lot of structure. So for example, there could be like uncertainty or multiple time periods. And then we tend to impose kind of structural constraints on preferences to sort of respond to this. So for example, we might want preferences to maximize expected utility, which is what I talked about on Tuesday. But in a general context, if you're just looking at sort of a simple decision over a family of abstract alternatives, we basically think of all preference orders as being equally valid, right? This is kind of the principle of the gustibus non est disputanda. And indeed, in general, in economics, the sort of standard view is that rationality just is preference maximization. But the sort of starting point of this project is to kind of question this account, right? Because it doesn't really seem like an entirely satisfactory account of what rationality means. Because the problem is that if an agent has no choice over her preferences, then there's a sense in which she's not really truly autonomous, right? So as I said, in economics, a rational agent, if you're rational, what you should do is maximize your preferences. But if you think about it, nobody ever asked you if you wanted to have those preferences. But this raises kind of a deep philosophical question, because what does it even mean to talk about choosing your own preferences? On what basis would you make that choice? According to the standard economic account, you make rational choices by maximizing preferences. So if you were going to choose your own preferences, you have to do that on the basis of a second order preference order. In other words, a preference relation over preferences. But then, of course, this raises the further question, where do these second order preferences come from? So presumably to rationally choose your second order preferences in an autonomous way, you would have to have a third order preference, right? And yes, you can already see that there's a risk of running into kind of an infinite regress. So there seems to be something kind of problematic here, right? So the idea of this project is to try to sort of formalize these ideas by introducing some notion of higher order preferences. So let me sketch out a simple model first. This is actually not the model which is the subject matter of the talk, but it kind of sets the stage, right? So for any set S, let PR F of S denote the set of all preference orders on S. So that's a notation I'm going to maintain through most of the talk. So now suppose that X is some set of possible outcomes. These could be consumption bundles or like ways that your life could go or something like that. So a first order preference is just a preference order on the set X itself, which we can indicate with a little subscript 1, right? And so a second order preference is then a preference order on the set of all first order preferences, right? So technically it's an element of this space here. So we can indicate that with a subscript 2. So if you imagine a rational agent endowed with a second order preference, how would she function? Well, first she would pick the first order preference that was optimal with respect to her second order preference. And then she would pick the outcome in X that was optimal with respect to her optimal first order preference. Okay, so that's great. But as we already noted, there's a problem. Where does the second order preference come from? Presumably it comes from some third order preference, which is the preference order on the space of all second order preferences, which we can indicate with this little subscript here, right? Okay, so you can start to see the problems of this approach. The first problem is that we can repeat this whole process ad infinitum. It never really converges to anything. A second problem, kind of a more technical problem, but nevertheless an important problem, is that many elements of this set of abstract preference orders might be infeasible for certain reasons. So for example, in economics, it's very common to assume that the space of outcomes comes with some kind of a topology, and then we require preferences to be continuous with respect to that topology. And the reason for this is because a small change in the outcome should not cause the agent's preferences to radically change with respect to that small change in the outcome. So there's a sense in which continuity is almost like a rationality condition, right? But there's a kind of a deeper problem, a kind of a more conceptual problem with this entire approach, Okay, which is that in the example I just gave you, we assumed that there were separate preferences over outcomes and over first order preferences, right? Those are two separate pieces of data, but that's not how rationality works, right? Rational agents do not form separate preferences over different aspects of the situation. They form holistic preferences over the entire situation taken as a whole. So here's a simple example to illustrate that. Suppose that there are two agents, Scott and Bob. Okay, so Scott prefers Scotch over bourbon, and Bob prefers bourbon over Scotch. So therefore, we could make a statement like Scott prefers Lagavulin to Buffalo Trace, whereas Bob prefers Buffalo Trace to Lagavulin. Okay, that's fine. But it's also meaningful to ask the question, would it be better to have Scott's preferences with a tumbler of Buffalo Trace, or would it be better to have Bob's preferences with a low ball of Lagavulin, right? So a complete description of the preferences in the situation would look something like this. It would say, having Lagavulin together with Scott's preferences is better than having Buffalo Trace with Bob's preferences, which is better than Lagavulin with Bob's preferences, which is better than Buffalo Trace with Scott's preferences. Right, that is the kind of statement we want to be able to make. So this suggests that the second order preference shouldn't just be a preference order over first order preferences. It should be a preference order over ordered pairs consisting of an outcome together with a first order preference. And likewise, the third order preference should be a preference order over ordered triples consisting of an outcome, a first order preference, and a second order preference, where the second order preference itself is a preference order over ordered pairs consisting of an outcome and a first order preference. Okay, so you can see that this is starting to get kind of complicated and ugly, right? So those last two problems I talked about, they can be addressed by developing a much more complicated kind of hierarchical model of preferences, and I've done that in some other work. But what I'm going to do today is kind of short circuit that entire approach and look at a different model, a recursive model, okay? So in this recursive model, agents can choose from a set of possible types. So what is a type? A type is kind of a jargon in economics. It's like whatever data encodes the agent's kind of like psychology, personality, something like that, okay? And so each of these types determines a preference order over type outcome pairs, okay? Which means that each type kind of indirectly determines preferences over other types. And since the types themselves determine the preferences, this means that each type implicitly determines a preference order over preferences. And this is the way that we capture the notion of higher order preferences without building a big infinite hierarchy. So that's basically the plan. So now let's get started with the technical details. So as before, X is going to denote some menu of possible outcomes. This is going to be fixed throughout. There's just some menu X of possible outcomes, consumption models, or whatever. Now we introduce a new ingredient T, which is a set of possible types. Okay, so a simple preference structure for T over X is a function Q that maps every single type into a preference order over X. Okay, so basically for every type little t, we get a preference order, which I'm going to indicate like this, over the set of possible outcomes. This is a very common model in economic theory. It's used in the theory of Bayesian games and the theory of mechanism design, etc. Okay, but this is not what we want. We want something a little bit more complicated. So here's the key definition. A recursive preference structure is a function P that maps every type into a preference order on type outcome pairs. Okay, so that means that for every single type T, we get a preference order, which I'm going to indicate with this symbol here, on the Cartesian product T cross X. All right, so what's the interpretation of this? So for any two types T1 and T2, and any outcomes X1 and X2, if type T prefers T1 X1 over T2 X2, what this means is that type T would prefer to be of type T1 with outcome X1, rather than being type T2 with outcome X2. Like, I'd rather be Scott with the Lagavulin than be Bob with Buffalo Trace, right? Okay. Now, notice that any recursive preference structure induces a simple preference structure in a very obvious way. Given any type T and any outcomes X and Y, we can say that type T prefers X over Y if type T prefers to be type T with outcome X rather than being type T with outcome Y. All right, so let's look at a simple example just to fix ideas. So in this example, there are three outcomes, which are indicated by three shapes, star, diamond, triangle. And there are four types, which are indicated by the four colors here, red, orange, green, and violet. So a type outcome pair is just a type, it's just a shape with a color. Okay, so here's a recursive preference structure. So for each of the four possible types, the four colors, we get a preference order over these colored shapes. So type red thinks red star is better than orange diamond, which is better than red diamond, which is better than green triangle, etc. Right? And we can read off the simple preference structure by just looking at each type's preferences over shapes of the same color, right? So red type thinks star is better than diamond, is better than triangle. Orange type thinks diamond is better than triangle, is better than star, etc. So we get our nice recursive preference structure and simple preference structure like this. Okay. So you can ask some interesting questions about this model. What I'm going to be focusing on today is something I call full autonomy. So to motivate the problem of full autonomy, suppose that we have some recursive preference structure like this. And suppose that there's some target preference order on type outcome pairs. Okay. Now, I'm going to say that that target preference order is P realizable if there is some type T which has those preferences. Okay, so now we can see the problem. The problem is that the set of P realizable preferences might be very small, right? So for example, this function P could just be a constant, right? Like that's allowed. There's nothing that says it can't be constant. Even if it's not a constant, it might be that all the P realizable preferences induce the same first order preferences over outcomes. Okay, that would be very frustrating. It would completely defeat the whole purpose of this model. The whole idea was to give agents lots of autonomy so they could choose their preferences. So, but if the sort of image of the function P is very small, then this agent in the end doesn't really have very much autonomy at all. Okay, so we don't want this. We want basically the opposite of this. What we want is a recursive preference structure where the set of P realizable preferences is very large. Okay, perhaps we'd like it to even include every feasible preference order over type outcome pairs, where the word feasible means whatever you want it to mean, like continuous or something like that. Okay. So in this case, we could say that this agent is really fully autonomous. So by choosing the appropriate type, she can realize any preference order she wants on type outcome pairs. Okay, so the question is such a thing even possible? Okay, and the answer is yes, under some conditions, under a suitable interpretation of the question. So suppose that the type space and the outcome space are metric spaces. Okay, and now what we're going to do is we're going to look at the set of all continuous preference orders on type outcome pairs. So as I mentioned earlier, there are good reasons why we would want preferences to be continuous with respect to the topology on the space of outcomes. Okay, so we're looking at this space of preferences now. So this space itself is a metric space when endowed with the Hausdorff metric. So now we come to our first result. For any compact metric space X of outcomes, there exists a metric space T of types and a continuous surjection P mapping types into continuous preferences over type outcome pairs. Okay, so such an agent is fully autonomous because in principle, she can have any preference order in this set of continuous preference orders by choosing the appropriate type. Okay, great. So mission accomplished, right? This is pretty good, but one could argue that there are some shortcomings with this theorem. It's not entirely satisfactory, okay? So first of all, as you've probably noticed, it only applies when the space of outcomes is a compact metric space, okay? However, the type space in that theorem is not compact. I didn't tell you that, but the type space is actually a complete mess, okay? Topologically, it's very nasty. Now, another problem is that this function P that I described, it's surjected, so we get this full autonomy, okay? But it's not injected, okay? So why do we care? Why does that matter? Well, what this means is that many different types map to the same preference order. Okay, but the agent could still be non-indifferent between these types as if they differed in some like invisible non-preference attribute. Okay, that's not really what we want. The whole point of this model was to give an agent preferences over her preferences. Now she has preferences over these types based upon some other information which we cannot observe, we can't control, we don't know what it is. Okay, so it's not really very satisfactory. A more philosophical observation, but nevertheless important, is that arguably an agent should be able to adopt incomplete preferences if she wants. So there's a big debate in decision theory about whether rationality requires that you have complete preferences, but there's certainly, a substantial literature in philosophical decision theory arguing that under some conditions, it's appropriate, it's rational to actually have incomplete preferences. And finally, a kind of a more ambitious goal, arguably to be fully autonomous, an agent should be able to adopt not only any preference order, but she should also be able to, in some sense, adopt any recursive preference structure. So what I'm going to show you now is a model, a theory of universal recursive preference structures, which sort of satisfies these desiderata. But first, we need some more mathematical machinery. All right. So now we're into part 2. All right. So recall that a strict partial order is just a transitive antisymmetric binary relation. So any partial order on a set X, of course, corresponds to a subset of the Cartesian product X cross X in an obvious way. Now suppose that X is a topological space, okay? So in that case, a partial order is continuous if it corresponds to an open subset of the Cartesian product X cross X. And if you think back to your familiar examples, you will see why this is the right definition of continuity for a strict partial order. All right, so I'm going to be looking at a kind of a slightly more complicated concept, what I call a local continuous partial order. So this is an ordered pair Y relation where y is a closed subset of x, and where the relation is a continuous partial order on y. Okay, so basically the idea here is that y is kind of like the domain of the preference. So it's kind of like things outside of y, for some reason, the agent regards them as sort of off limits. Maybe they're kind of like she's not aware of them, or they're inadmissible for some reason. All right, so let P of x be the set of all local continuous partial orders on x. So what I want now is to define a natural topology on this set. Okay, so to do that, first of all, observe that for any local continuous partial order y relation, we can define a set like this. I'm going to use this notation. This is a set of all ordered pairs x, y in the Cartesian product y cross y, such that x is not preferred to y. All right, this is a closed subset of y cross y because its complement is open because the relation is continuous, and therefore it's a closed subset of x cross x because y itself is closed in x. Why do we care about that? Because of the following. For any compact Hausdorff space x, if we look at k of x instead of all closed subsets of x, then there is a natural topology on that space called the Pivato topology. Okay, if x was a metric space, a compact metric space, then this corresponds to the topology of the Hausdorff metric. But this is well defined even if there's no metric. Okay, so if you recall on the previous slide, I showed you that there's a natural mapping which takes every local continuous partial order and identifies it with a closed subset of the Cartesian product x cross x. So now we can use that to define a topology on the space of local continuous partial orders. We simply pull back the Pivato topology through this natural mapping. Okay, and we get a topology on the space of local continuous partial orders, which I call the co-Pivato topology. All right, so why is this a good idea? Well, because it turns out that this topology has some very nice properties. Okay, if x is a compact Hausdorff space, then the space of local continuous partial orders is also a compact Hausdorff space. So now we're motivated to kind of slightly modify the definition of recursive preference structure. Here's our new definition. Suppose that x is a compact Hausdorff space of possible outcomes. A recursive preference structure over x is an ordered pair T phi, where T is another compact Hausdorff space of possible types, and where phi is a continuous function from T into the space of local continuous partial orders on type outcome pairs, where when I say continuous, I mean with respect to the co-Pivato topology. Okay, so this is the definition of recursive preference structure we're going to be working with now. All right, so the next thing we need is we need a notion of morphism of recursive preference structures, right? And so to define this, I need a little bit further mathematical machinery. All right, so let x and x primed be two compact Hausdorff spaces, and suppose that psi is a function mapping x into x prime, which is continuous. So for any local continuous partial order defined on x, okay, I can generate a new local continuous partial order on x prime, which I'm going to call y prime relation prime as follows. Okay, so y prime is just the psi image of y. Okay, this is a closed subset of x prime y. Well, because the function psi is continuous and these are compact Hausdorff spaces. What about this relation? The relation prime is defined as a partial order defined as follows. For any little x prime and little y prime, I will say little x prime is prime preferred to little y prime if and only if x is preferred to y for all x in the psi pre-image of x prime and all y in the psi pre-image of y prime. Okay. And so basically, let's call this new guy here psi Pilcrow. This is the psi Pilcrow image of y relation. So this construction yields a function psi Pilcrow, which maps every local continuous partial order on x into a local continuous partial order on x prime. Okay, why is this a good idea? Well, because this function is very well behaved. Okay, if the original function psi from x to x prime is continuous, then this Pilcrow transformation is a continuous transformation, a continuous function from the space of local continuous partial orders on x to the space of local continuous partial orders on x prime. All right. So now we are ready to define morphism. So suppose that I have two recursive preference structures over x. So T1 phi1 and T2 phi2. And suppose psi is a continuous function from T1 into T2. Okay. Let I sub x be the identity function on x. So let's bundle those things together and we get this Cartesian product psi cross ix. This is a function from T1 cross x into T2 cross x defined in the obvious way, right? Okay, now we apply the Pilcrow transformation to this Cartesian product. So we get a new function, which I'm going to write as psi dagger, which maps from the space of local continuous partial orders on T1 cross x to the space of local continuous partial orders on T2 cross x. So here's the definition. The function psi is a morphism of recursive preference structures if the following diagram commutes. So what is this diagram telling us? It says if we start with a type in T1 and we first transform it into a type in T2 by applying psi, and then we use phi2 to obtain a local continuous partial order on T2 cross X, we get the same thing as if we started with the same type in T1. First, we apply phi1 to get a local continuous partial order on T1 cross X, and then we apply this weird induced mapping C dagger to convert that into a local continuous partial order on T2 cross X. All right. So at this point, most of you have probably figured out what's going on here. So let me pull back the curtain and reveal what's actually happening. So let CHS be the category of compact Hausdorff spaces and continuous maps. Okay, as you have probably figured out by now, what I've just basically finished telling you is that there's an endo functor P on the category of compact Hausdorff spaces, which transforms every space X into the space P of X of local continuous partial orders on X, and it transforms every function C into this function C Pilcrow, mapping P of X into P of Y. Okay, so that's clearly endo functor. Now, let's suppose we fix a compact Hausdorff space X, again, of possible outcomes, okay, and consider the Cartesian producting endo functor on compact Hausdorff spaces. You just transform every space T into the Cartesian product T cross X. You transform every function C from T into S into the function C cross the identity function from T cross X into S cross X. Another endo functor. Now let's compose them together to get an endo functor Rx. So this is just an endo functor which takes any space T and transforms it into the space of local continuous partial orders on T cross X. Okay, so clearly what I've been calling a recursive preference structure is just a co-algebra for this function, right? And what I've been calling a recursive preference structure morphism is just an Rx co-algebra morphism. So now we're in the land of co-algebras. Great. Okay, so now suppose that X is a compact Hausdorff space and let T hat, phi hat be a recursive preference structure over X. So here's the key definition, which motivates the title of the presentation. T hat, phi hat is a universal recursive preference structure over X if it is a terminal object in the category of recursive preference structures on X. Okay, so of course what that means is for any other recursive preference structure T phi over X, there is a unique recursive preference structure morphism psi hat mapping T into T hat. Okay, all right. And since I've just finished saying that these are co-algebras, I could equivalently say that a universal RPS is a terminal object in the category of Rx co-algebras. Okay, why is that a good thing? Because terminal co-algebras are awesome. Okay, so here's the key proposition. Suppose that T hat, phi hat is a universal recursive preference structure over X. Okay, then of course Lambek's theorem tells us that the function psi hat from T hat into P of T hat cross X is a homeomorphism. Okay, and furthermore, the terminal co-algebra, if it exists, the universal recursive preference structure, if it exists, is unique up to isomorphism. So if T tilde phi tilde is another universal recursive preference structure over X, then there's a unique isomorphism from T hat, phi hat, T tilde phi tilde. Okay, so why is this relevant to us? Part A is saying that this universal recursive preference structure is fully autonomous, right? This function phi hat is surjective, so every possible preference order can be realized by some type. And it has no redundant types because this function phi hat is also injective. So every single preference order is realized by exactly one type. So the problem I mentioned earlier goes away. The fact that this bijection is actually homeomorphism is just a bonus. Part B means that the universal recursive preference structure, if it exists, is unique up to isomorphism. So we can talk about the universal recursive preference structure. Okay, so now of course the million-dollar question, this miraculous object with all these great properties, does it even exist? And that's the main result. For any compact Hausdorff space X, there is a universal recursive preference structure on X, and the type space of this universal recursive preference structure is also a compact Hausdorff. So it's got a nice topology. And in fact, the topological properties of the universal recursive preference structure kind of can be derived from the underlying space of outcomes. Okay, so if X is metrizable, then the type space of its universal recursive preference structure is also metrizable. If X is a continuum, then so is the universal recursive preference structure. If X is a Cantor space, then so is the universal recursive preference structure. And if X is a finite set with a discrete topology, like the silly example with the three shapes, okay, then the type space of the universal recursive preference structure is a Cantor space. All right, I'm almost out of time. I'm just going to walk you very quickly through the proof. Okay, this is the standard construction for those of you who know about coalgebras. Okay, so we construct a chain. T0 is the 1-point space, which is the terminal object in the category of compact Hausdorff spaces. T1 is its image under the functor. Okay, T2 is the image of T1, T3 is the image of T2, etc. What about the maps? Phi0 is just the unique terminal morphism. It maps everything to the 1-point space. Okay, Phi1 is the image of Phi0 under the functor. Phi2 is the image of Phi1, etc. Okay, so now I have an infinite chain. Okay, let T infinity be the limit of that chain in the category of compact Hausdorff spaces. Okay, now here's the key fact. This is the key technical lemma. The functor that I constructed that creates these recursive preference structures, okay, preserves omega limits. So therefore, that means that there's an isomorphism from the Rx image of T infinity, which is just the Rx image of this limit, into the limit of the Rx image of the chain, right? We can commute the limit with the functor. But of course, the way this chain is defined, Rx of Tn is Tn plus 1, Rx of Pn is Pn plus 1, that was what I just said. Okay, so therefore, the Rx image of the chain just is the chain. Okay, so therefore, the limit is just the original object back again. So we putting it all together, reading from beginning to end, we get an isomorphism from Rx of T infinity to T infinity. Let's give that isomorphism a name. Let's call it phi. So phi is a function from T infinity to Rx of T infinity. So just by construction, it's an Rx coalgebra. And now a theorem by Yuri Adamek says that this construction yields the terminal Rx coalgebra. That's how the proof works. All right, so just to wrap it up. So to incorporate notions like autonomy or responsibility to a model of rational agency, I've argued we need some notion of meta preferences. Formalize this, I introduced recursive preference structures. In a topological setting, you can construct a fully autonomous recursive preference structure. And furthermore, there exist universal recursive preference structures, which are the terminal coalgebras of an endofunctor on the category of compact Hausdorff spaces. So thank you very much.
Do we have any questions for Marcus?
Thanks for that. So from your understanding, is that this terminal algebra is converted to X, is that correct?
Yes.
So then this have applications.
I didn't hit the last part.
Does this fact have implications or interesting consequences?
The fact that it's factorial in X? I don't know. Probably, usually that fact has useful applications, but I don't know yet. That's a good question.
Thanks very much, Tom. The simple modular types, you mentioned it's not just using decision theory as the foundation of Bayesian game theory and speculative design and auction theory, so it's next speculative successful definition. Do you think there's hope that this could also kind of make a jump to game theory and those things?
I haven't investigated that. I mean, my motivation for this project was mainly philosophical, right? Sort of examining these issues of autonomy, sort of more normative. It's conceivable it could be used in game theory. I mean, there is a literature, there is a kind of a literature in descriptive decision theory dealing with agents who want to modify their types over time. So for example, there's literature on what's called temptation. So temptation is about the idea that, like, you know, you don't buy the bag of Doritos because you know that if you buy it, you will eat the whole thing in one sitting, right? And so that the literature on temptation is kind of related to this idea that agents might have some attitudes about what their preferences are going to be tomorrow morning. Something like this could be used there, but I haven't really investigated that idea.
Maybe one more sentence.
Well, I mean, this is, I guess you're aware that there have been various constructions of final co-algebras of type spaces by Moss and Glitzer and so on. I just wonder if there are any connections, differences.
So that's a fantastic question. So that paper, the Moss and Glitzer paper, was kind of the inspiration here. Okay. So they constructed a final co-algebra. Basically, it was a kind of like a categorical reconstruction of an object which already existed, the so-called universal type space in Bayesian game theory. Okay, what's the difference? The key thing there is types define not preferences, but beliefs. Agents have beliefs about other agents. Okay, so the functor there, the endofunctor that you're constructing a co-algebra of, is basically like a probability endofunctor. Okay, so that functor is well defined, it's well established, it's got lots of nice properties. the kind of key issue here was that we're not using that functor. We have to invent the new functor, which assigns to each space a space of preferences. Okay, and the obvious way of doing that doesn't work because the obvious way of doing that is not a covariant functor, it's a contravariant functor. And so then you can't do this whole co-algebra thing, right? So basically, sort of the kind of big innovation here is to actually like invent a covariant functor of preference spaces, prove that it has nice properties like, you know, preserved along with the limits. And then at that stage, you can basically do something like what Moss and Villiers did. So that's the relation between the two.
So in the interest of sticking to the schedule, I should take further questions after the session. Let's thank the speaker again.